So thank you all for joining us for the review session for the lecture by Irene Beyerlein on twinning in metals. Irene, please take it away.
Yeah, thanks, Mike. So thank you all for coming back and joining us this morning or afternoon, depending on where you are. So I had where we last left it in the lecture on Monday was to end with two types of points of discussion. One is to just simply continue with any questions that anyone had from the last lecture. So we're happy to go through those. And the second set of discussion points were cast in terms of 3 questions. And I list them here. Here's the first one, second one, and third one. So I just read them out for now, and then we can go back and see, go back to the first set. And I right now with this screen, with this PowerPoint here, this does not belong to the lecture I gave last Monday. But I can certainly, for questions on the last lecture, bring up those slides. But just to finish this, the 3 questions were to identify at least 3 ways deformation twinning is different from plastic slip. And the second question is to list and discuss at least 3 types of slip-twin interactions. And then the last one was to describe 2 or more ways properties of deformation twins can affect macroscopic response. Now, some of these answers are in a way embedded in the discussion that I gave on Monday. So these aren't meant to be trick questions or anything, but just sort of to catalyze more discussion. So with that, start with any questions anyone had from the last lecture. I don't know if you could speak up, or I think last time I recall there was a chat or a space in which people could type questions.
There's only 16 of us, so I suggest if you have a question, simply unmute yourself and speak it clearly into the microphone so we can all hear you.
Okay, yeah, that would work best for me. Totally don't mind that.
Sure. Dr. Demkovics, can I go first?
Yeah,
sure.
go ahead.
Yeah.
Hi, Dr. Beyerlein. Good afternoon.
Hello.
And so the first question that I have is that throughout your slides, we looked at twinning from a deformation and a dynamic deformation perspective. What would be a proper way to thermodynamically quantify twinning?
So to quantify twinning in what ways? So if you were to say you want to determine shape, for instance, I would think of going back to some of the classical work by Orwan and later by Manu, and some others have then helped to use DFT or MD to define some parameterized idea. But the theory would be that the shape is determined by a balance between the elastic energy that the twin the twin shear provides and the interfacial energy between the twin matrix interface. And then you can then think of how then shapes would be different if you had different twin modes, because they would each provide different elastic energies. And the interfacial energy would also then change as well with different twin modes. And so this would be one aspect of twinning.
Okay.
Yeah.
That does answer my question. Thank you.
Okay.
The second one that I have is that earlier in the slides, it was mentioned that twinning is the second easiest deformation mode.
Yes.
Yeah. So is it relevant just to HCP materials, or is it relevant to FCC and BCC as well?
So I wouldn't say that it's the second easiest in the sense of for cubic materials. The point with the HCP that's interesting is that with HCP you necessarily need to have different slip modes in the crystal in order to accommodate a general deformation. So there's the A slip and C slip, and because of the atomic arrangements and density differences between A slip and C slip, that C accommodating slip modes like C plus A are necessarily harder. So it's easy then to make the conclusion that twinning could possibly lie between basal or prismatic A slip and, let's say, pyramidal slip. Now, that's not true for all HCP metals. I'm thinking that when you alloy a metal, you can alloy it so that C plus A slip becomes easy. And then if it becomes so much easier, like let's say Ti-64 is an example of this, or Ti-7 aluminum. The pyramidal slip in that case is so much easier that you don't see twinning in that sense. Now, when you go to something like FCC, and BCC materials, the twin plane is shared by a slip mode, so that's different. So you have now for FCC, the twinning mode is twin plane is 111, just like the slip system. And then with BCC, while BCC deforms by multiple modes, let's say 110 plane and 111 direction, or 112 plane and the 111 direction, or 113 modes, which is the 112 plane and the 111 direction, those slip modes, that also shares a slip plane with twinning. So in a way, it's a different story because the twin plane and slip modes share the same plane. The twin and the slip modes share the same plane.
Okay. Does answer my question. Thank you. And the third one that I have is sort of like it goes on a tangent, and it's something that I was thinking maybe the wrong approach, but let's go over it anyway. So like in twinning, the local rearrangement or shifting of atoms like sort of gives a flashback of martensitic transformation, right? And I'm not trying to establish a connection here, but could we call twinning as a diffusion-less transformation, considering bearing in mind that we do not actually create a new phase as we do in martensite, but can we claim it as a diffusion-less or short-range transformation or short-range diffusion?
I think so, since it doesn't involve diffusional processes. It does involve some amount of atomic shuffling.
Yes.
And that's the case in all twins in HCP. Yes. That and the amount of atomic shuffling varies with different slip modes. And so and that does it does affect strongly the kinetics. So for some time there was a argument over what's the step height for the twinning dislocation. So because that does govern in a way the transformation between the matrix and the twin, is the step height of the twinning dislocation. So, and what ends up prevailing is that the step height is as short as it can be. The shorter that step height, the less atomic shuffling you have, but the higher the elastic energy or the Berger's vector between the planes. And what ends up happening is just easier for the twinning dislocation to move if it has less atomic shuffling. So it is affected by the atomic shuffling part of the transformation.
Okay, sure. Thank you very much. That does answer my question. Yeah. Yeah. Thank you. That's all from me.
Oh, okay. Thanks. Thank you.
Hi, hello.
Hello.
Can you hear me? Okay, great. Sounds good.
Yeah.
So I have a couple questions. So first is that usually the lecture said that the twinnings occurred after sleeps. So when the sleeps are not easy, the twins are formed. So as far as what I understood is that this is also a thermally activated process. And usually for this type of process, the Arrhenius equation, that the exponential form equation, come to play. So it is the form of equation used to describe the nucleation of twins.
So up to now, I don't believe it's been applied. The transition state theory has been applied to the formation of twins from slip to twinning partials. So while I mentioned that twins follow slip, that concept is relatively new. So it's not that it's been, so it's, and a lot of it's come from atomistic simulations that emerged with that technique later on. So and so with that, it hasn't been applied. So that's maybe an idea that could be pursued. I think but it hasn't been. There are other things to consider, however, in that that one needs to have also a way of stopping the dislocations, probably more so than, so it's not that the dislocation is moving and then temperature then will cause a transition. That they're part of the process that at least we're finding in the recent times is that the dislocation has to be stationary in some way. So that doesn't change the question you asked, but it was just more of a thought that I wanted to share, is that there may be other steps in that process. But if you're interested in modeling twinning, then it's not a bad idea to think of, at least as a first step, to apply the Arrhenius equation or expression to it.
Okay, thank you. And second is that for nucleation, so what I understood is that nucleation is basically the generation of a new phase. So if there's anything wrong, please just correct me. And so how to physically understand the nucleation of twinning?
So some of the newer ideas. So I had mentioned earlier that the nucleation process was at first thought of as originating from a single dislocation, and that dislocation would dissociate and create one twinning partial. That idea has prevailed for FCC and BCC in cases, as I mentioned earlier, that the twinning dislocation shares the same plane as the slip dislocation. So it was a planar dissociation reaction. So that taking that idea and moving that to a HCP where you have a non-planar dissociation does also engender the idea that you can have a single dislocation be involved in then producing one twinning partial, and then they sequentially glide on adjacent planes. However, in the last decade or maybe even 15 years, there's been some work to show that actually, in order to create a critical nucleus, you need to have involved a coordinated motion of several defects on adjacent planes, so that a stable embryo then needs to form. So it is a stress-induced reaction that then causes a shuffling motion within an embryo to create then that twin embryo. And then beyond that, then it's possible then to have a sequential glide of twinning disconnections on adjacent planes. But that first event is involves atomic shuffling within a cluster of adjacent planes, and that number has yet to be decided. But some atomistic calculations show that it can be up to about 17 adjacent planes, so it's sizable.
Okay, thank you. And once a twin is formed, what would be the stress field or strain field for that twinning?
So that has been studied in various ways. That if we were just to take the simple case where you have a twin lamellae or even a twin embryo embedded in a single crystal with no applied stress, that twin, due to its twin shear that it creates, will generate a stress field around it. And the finding is that since within that domain of the twin, there's a well-defined plane and shear on which that shear occurs. So almost like a mode 2 crack, in front of that, the crystalline material in front of the twin will experience a stress concentration. On the lateral sides where the twin boundaries are, that's, let's say, above or below the mode 2 crack or lamellae in this case, there's also stress concentration, but if you were to project that onto the twin boundary, you'd find that it is in the anti-twinning direction. So we call that a backstress. So the stress fields around a twin are quite heterogeneous, where you have in front of the twin, you have a stress concentration, and on the sides, you have almost a backstress. I could, let's see, I could share the screen. We do have some calculations of that. If others are interested, let's say, I guess in the spirit of this, let's see if I can, let's see, let me put up here. My computer's a bit slow. We have, I think I ended maybe near the end of the talk last time. So here, if we take a crystal, apply stress, we see that the stress is uniform. In this case, I believe this was a zirconium crystal. We have anisotropic elasticity, crystal plasticity. It's average 20 megapascals if we were just to take the stress tensor at every point and resolve it on the twin plane in the twin direction. And then if we were then to, within this deformed crystal, while it's under deformation, insert a twin, the twin here, let me, I'm not sure if anyone can see my arrow, so let's use a pointer. The twin here is entirely embedded within the crystal. It's still under applied load. We then, now I'm just showing a contour map of the stress field around the twin, as we have described the stress field by a certain component, and that again is we just selected it arbitrarily to show the component of the stress projected onto the twin plane in the twin direction. And so we see here that anything that's color, it's heterogeneous. That's the first thing that we see. when it started off is homogeneous under deformation before the twin. Now we've colored things in a particular way, such that if that projected stress is negative, then it's got a blue color. If it's red, then if it's positive, then it's red. And the reason we do that is that since twinning is a highly directional a mechanism, that if it's blue, if it's negative, that means that the stress is acting in the anti-twinning direction, which means that it would not promote further growth of that twin. If it's red and positive, then it's in the twinning direction, and even more so if it's a dark red, so it's not this light, anything that's this sort of whitish light color is below the stress that it was before the twin, which was about 20 megapascals. So anything above it, you've now, by introducing the twin, you've locally increased the stress field, such as like at the twin tips, you've increased the stress field beyond what it was before you introduced the twin. And so provided that twin has grown into an embryo, and as it grows lengthwise, it's then creating its own stress field that would promote its continued growth. But along the twin boundaries, and even around that twin boundary, you can see that it's an anti-twinning stress field, so it would not thicken as it grows.
Okay, so based on this, I'm thinking about, so for dislocation, usually the mechanism for dislocation to harden the stress strain curve is by inducing the dislocation density, to say, so the material got saturated because of the height of dislocation, the stress strain curve got hardened. And also you showed a stress strain curve got hardened before by both slip and also twinnings. So here it seems that we do not require that much on the density of twins for hardening the stress strain curve, because even though for this single twin that it can, improve the magnitude of stress locally. So basically, how does twins contribute to the hardening? Like, how do you understand this process? Or by the density more, or just by single twin?
Right. So actually, this gets into some thoughts. Your thoughts here pertain to one of the questions that we are going to discuss, and so it's fine with me if we go right into it. It was the what is the effect? What are some effects of slip twin interactions? And I believe that was the second question that we could discuss. So we can discuss it now. That there are two slip twin interactions that right away immediately can contribute to a twinning. In slip in a profound way. So one is that this twin region here will reorient the crystal. And another is that when the twin forms, it introduces a boundary. So as far as the reorientation part, that then changes the reorientation of that domain with respect to the load, which then could favor different types of slip. You could imagine you would get a softening if the slip that the new slip that was invoked is softer than the one that prior to that. That's possible in HCP materials because different slip modes have vastly different critical resolve shear stresses. Another way is just by introducing the boundary. So by introducing a boundary, you make it you disrupt the crystal orientation, which means dislocations have to then that like to glide on one particular plane, they then have to change their course, and then that there's extra energy in order to have that slip transfer across that boundary. So those are two ways to harden. Now, we asked if there was three ways for slip twin interaction, and one is one that we could think of here. There's actually many. I just mentioned three to think about. But as you point out here, here's this high stress concentration. This stress field is different than the stress field prior to the twin. And that could also locally induce different kinds of slip as well. So I could probably, let's see, I'm going to see if I can have a better way of illustrating some of these things. So as far as slip twin interactions, if we take this picture here, we have a grain with multiple twin lamellae, let's say, that have formed. They've reached and are connected to the grain boundaries. And these twins, as I've delineated here, just let's say we pick a particular slip plane, and because of the reorientation that's caused by the twin lamellae, that the same slip plane may appear differently in the matrix. So in the twin and the matrix, they would cause a reorientation of that plane. So by reorienting parts of the grain, you could then initiate a different type of slip within those twins, and that slip could be either more or less favorable. So that could affect slip in one way. Also, a second way has to do with again this idea of a barrier effect, that the twin boundaries act as directional barriers. So the twins then restrict the mean free path of a dislocation. So without the twin, let's say slip would have been favored on this plane here, it would have had a longer mean free path without the twins. But then once the twins get introduced, its mean free path is shortened. And something about twins is that as you deform the material, the number of twins within this grain can change. The thickness of these twins can change. So you can then see how twin slip interactions would evolve as the twins change morphology and number and volume fraction. So for instance, if the twin decided to grow just with strain, then you could see that the volume where a new slip activity is favored, which is the twin now is favored a new twin activity, that volume will increase as the twin increases. Also, as this twin increases, the matrix shrinks. And as the matrix shrinks, the mean free path of any slip that would have been favored originally in the matrix has now increased. So, and there's several very, I would say, strong slip twin interactions. So I like the third one that you brought up, which was the stress concentration in front of a twin could also change slip within that twin tip plastic zone, so to speak. So.
Okay.
Thank you. So yeah, that's.
Yeah, thank you so much. Just one more question is that because you mentioned uniaxial tension or compression, that's the tests usually required to do this test to induce the twins. Given the direction, it seems the direction of loading is significant. I mean, the relation between the direction of loading to the direction of twins. And for this compression or tension, they are usually uniaxial case. So first, could you please compare between these two tests, whether it's tension or compression, does it affect much on the production of twins? That's first one. Second, so in order to induce some inhomogeneous deformation field, how about indentation? Because indentation, that even though it is still most of them are compression, but are more complicated than uniaxial tension. So did you do any tests by indentation? So these are the two questions.
Yeah. So actually, what's important for identifying how much twinning occurs and is that you need deformation, but it's not so critical that it has to be a particular type of deformation test. So I like to use the example of uniaxial compression or tension because those tests are standards, so people have used them frequently, right? But they're certainly not the only tests that can induce deformation twinning. So your idea of indentation is also possible. That if you have indentation where under the indenter you have several grains, then it's you're likely to see twinning in still those grains that were suitably oriented with respect to that local stress state that's applied to them. So there's absolutely there's the possibility to see twinning under an indenter for a polycrystal. There are also cases where folks have taken single crystals and applied an indentation to a single crystal. And in that case, the crystal would be suitably oriented with respect to the indenter that twinning would be invoked. So some that's also possible. So it's not I would say that the important thing is to if you want to see a statistically relevant amount of twinning, then it's important to have grains or the crystals oriented suitably so that the c-axis would either be in plot, so that the c-axis would need to either contract or extend in order to accommodate the applied deformation. So in the examples that I gave earlier, there was a sheet material, and that sheet material had a strong texture, which meant that most of the grains were suitably oriented, or were oriented such that their c-axes, or this c-axis here, lay through the thickness of the sheet. So one can then imagine, well, if I were, how I could would cause most of those crystals to either extend along the c-axis or contract along the c-axis. And as I think about how to apply that load, and I want to apply it such that I extend the c-axis, then I am making that crystal prone to extension twinning, because extension twinning would be promoted because the grain would need to extend its c-axis. Or alternatively, if I wanted to promote contraction twinning, I would then apply the load to my texture or my material such that most of the c-axes would have to contract in order to accommodate the applied load. And then I would give it a situation where contraction twinning would be favored.
Okay, thank you so much. Sorry for my too many questions, but my last question, I just
that's the idea here.
just came to my mind. So I would like to quantify the contribution. Like, for example, that when we do experiments, we get a low displacement curve, and from that we get stress strain curve. So we observe the hardening of stress strain relation, and do we have any way to contribute to quantify the contribution from different hardening mechanisms like twins or slips? So one idea is that if we have any way that can take the image of the deformed material at each instantaneous time that we combine these two information, we know that how much different mechanism contribute to this hardening. But this may be not that trivial to do in reality. So do we have any way to contribute to quantify this sort of contribution of different mechanisms? Thank you.
Yeah, it's actually, that's one of the difficulties with twinning, is that if from the macroscopic stress strain curve, there even if you were here, I'm showing two examples of magnesium. This is polycrystalline magnesium and single crystal magnesium. Is that folks have tried to do that, right, by looking macroscopically and seeing what's going on, right? And if there were just one mechanism, then it would be easier to say, if it's just twinning, then I could get an idea of what the amount of twinning. But the problem with these materials is that twinning's not the only mechanism contributing to a macroscopic stress strain curve. Now, so qualitatively, you can get ideas of signatures of twinning. So this is an example where you have a polycrystalline sheet, and these are 3 stress strain curves that were obtained from that same sheet, but applied with different applied loading. So now you see in these 2 curves with the squares and with the open triangles that these 2 cases were different loading states. This is in plane tension. So this is opposite arrows here. So taking in plane of the sheet and applying tension to it. This is through thickness compression, so normal to that sheet. These stress strain curves, to me, if I were to look, you would not even think something funny is going on. You would think this is just conventional slip, because I have my hardening rate is decreasing with strain. However, when the stress state is in plane compression, which is as I've drawn here, that you start to see this all these inflection points in the stress strain curve that aren't normal. And so qualitatively, this has been connected with twinning and slip. So this is not a result of just twinning alone, but is the combination of twinning and slip. So you have now not only do the twins accommodate deformation, slip accommodates deformation, but the details of this flow stress strain curve also arise from slip twin interactions, like the hardening effects that we mentioned. So this from this curve, you cannot tell what's the volume fraction. You can't quantify volume fraction of twinning. You can't, because you don't know. You don't know what proportion of slip is also contributing. I show here also this case of single crystal magnesium. You see qualitatively similar behavior between that and the polycrystalline material. In this case, that in these 2 cases here, these in which there has been, this is a complicated confined compression test on a single crystal. This is a tension along the C-axis. This is also tension along the C-axis with different alternative boundary conditions on the transverse cases. But these inflection points on the stress strain curve look very similar to this one for the polycrystalline material. And qualitatively, they can be explained by the same kind of twin being activated in addition to slip. So what's been done is to, I think you had alluded to it earlier, that is to you can characterize by characterizing the volume fraction at each strain level, and you do see that the amount of twins have changed, but it's not that. What's interesting, it's not that the twin volume fraction increases steadily here, and that's not why this is coming about. A lot of it is that the twin volume fraction may even increase and saturate at this point, but then this hardening comes about because once they've grown to a certain thickness, you induce a harder slip mode. You induce pyramidal slip within the twin domains. And at the same time, the easy slip systems that were activated in the matrix are starting to get constrained by the twin boundaries. So this rapid hardening happens. So my point being that it's even if the twins were to saturate in volume fraction at this point, this hardening with continued strain could just be due to slip twin interactions. So other than doing microscopy, there's been a lot of modeling work done where it's important to take a crystal plasticity based model where you can have the crystallinity model directly and of the slip and twins, and to attempt to identify what are the proportions of twinning activity, slip activity, and different modes of slip contributing at every point in this deformation. So while I wish I could give you another answer other than, well, modeling has been a way of quantifying it and comparing that to experiment, but it's unfortunately it's not obvious by just looking at the stress strain curve exactly what relative amounts of slip and twinning are underlying the stress strain response.
Got it. Thank you so much. That's all my questions. Thank you.
Okay, thanks. So this is. So do we have any more? I think we last of the last one of the last responses dealt with slip twin interactions, and one of the discussion points today was to discuss 2 or 3 different slip twin interactions. We just discussed 2. Another one I wanted to bring up is that an interesting one. This is from actually a 2010 paper by Lei-Yun Wang et al. So I should have put the reference here, and so I'll put the reference here when we post these slides online. But another interesting slip twin interaction has to do with the formation of slip bands at the ends of twins. So he's seen several instances here where this is a commercially pure titanium, so it's HCP crystal structure. Some of the grains, such as grain 2 here, you see these nice twins that have formed. Now, as we discussed before, you don't know these are twins just by looking at them in this SEM, but once you identify the slip twin, the matrix twin orientation relationship, you can, across these, then you can be sure that these are twins. And so they did do that. But what's interesting is you can see right where the twin tips have intersected grain boundaries, that has initiated a series of slip bands within the neighboring grain. So for this particular neighboring grain, these twins in its neighbor had an effect on slip activity. Whereas you can see that these same set of twins have also impinged on this common grain boundary with grain 3. However, it doesn't look like grain 3 has been noticeably affected, as pronounced as this grain. I've also other different types of, are there other areas where the authors also saw similar slip to twin interactions? Is that here you have another grain that has these have been identified and verified to be bar 1, 2 twins, and then in the neighboring grain, it has triggered slip bands on a particular slip system. Here is another example. These are twins in this grain, and we see a nice, well-defined set of slip bands. Now, in this case, the twins may have affected where the slip bands occur, but you can see this also might have been the predominant slip system because these slip bands also impinge on this grain. So one could then conclude that it is possible that these slip bands occurred first, and then these twins happened or ignited in this grain. So just some interesting, another slip band, twin band interaction that I thought would be important to bring up. Here you can see these are slip bands, and these have been identified as twin bands in the neighboring grain. In this case, you see here that these twins have, and for some cases, the twins have formed and have reached the opposing grain boundary, but in some of these cases, it's stopped within the interior of the grain. This may suggest that these slip occurring in intense bands in this grain have then formed twins in the neighboring grain. So that's another interesting slip twin interaction. Did anyone?
I'm really glad that you mentioned this. I was actually going to ask you about it. So just a couple of quick questions about this. One is, if you look at that upper left figure and you look at grain 2, which is the one with the twins, is there any particular reason why the twins seem to be so regularly spaced there? That's number one. Number two, I think of the work of Tom Bieler, and I think he was working on titanium aluminum, where they saw that the grain boundaries where these twins intersected were the initiation sites for cracks. And that sort of struck me as surprising because I was expecting precisely this kind of thing to happen, where twins would have simply created slip bands in the neighboring grain, but they didn't see that. And I wonder if there's a good reason for it, or is it simply just because titanium aluminum doesn't slip very easily or something like that?
Yeah, that's interesting. So one thing to mention is that I believe Tom Bieler was one of the co-authors on this 2010 paper that I'm showing images from. And so in this case, it is interesting to see that you have such irregularly spaced twin bands. Now, why they form in this way is some thoughts on that are that let's say that the twins nuclei, because they start as nuclei and they're dispersed somewhere within the grains or at the grain boundaries, that you have many nuclei, but then the ones that actually manifest to become detectable in an SEM, then you're looking at the interaction between larger lamellae relative to interactions between tiny embryo. And when we've analyzed stress fields between parallel twins lamellae, that you find that that there's a back stress that's generated along the lateral twin planes. And that back stress we call it a back stress because it's an anti-twinning direction for that twin. So if you have another twin that's just like it, that's some distance from another twin, that you have this anti-twinning stress field between them. And so studies of parallel twins have found that as parallel paired twins get closer to one another, that the interaction stress between them is such that it enhances that anti-twinning stress. So it makes it even more difficult for twins to grow the closer they happen to nucleate. So, but the further away that interaction stress decays, and then the stress of twins far away beyond some critical spacing is such that it's as if they were alone. So, so what I'm saying is that if you were to imagine that you have twins that are embryos that are distributed, that as they grow, close twins that are grown together are going to be hindered from growing. But at some point, once they reach a certain critical distance, their interaction stress decay to a point that is as if they're just growing on their own. So that could be in a way helps to define some critical spacing that they would optimally be can grow apart from one another. But it definitely, if they're too close, then there'll be a competition for one of them to grow into a lamellae compared to the other.
Yeah, very interesting. Thanks.
Yeah. So that's a kind of some thoughts. Those are we had studied that with respect to stress field calculations around paired twins, and that backstress interaction that increases that anti-twinning stress between them and could potentially stunt their growth. That those stresses depend on elasticity and plasticity of the particular crystal. So one can then imagine that if I have different types of plastic behavior that in different crystals, different materials, that every material would have its own critical spacing between twins. That it also depends on the amount. It's also very critically dependent on the amount of twin shear within for that particular twin. So so then that would engender a different critical spacing for different twin modes. So I mean that's just some thoughts on the critical spacing. The other question you had was on Ti 7, or no, Ti aluminum. Ti aluminum.
Very metallic.
Intermetallic. Yeah. If so, yeah. First of all, I think it's neat that it twins. I don't know what's its crystal structure of this intermetallic.
I think it was cubic.
Okay. So if it's B2 or twins and FCC.
Yeah, that I don't remember. It could have. I don't remember.
Yeah. It's so just as a qualitative relationship is that usually the twins in the cubic system, the twin shear is extremely high, much higher than in the twins in HCP. So the stress concentrations ahead of those twins are much higher, and that may be one reason why they see cracks instead of plastic zones or plasticity. But that could explain why there's a difference there.
Thanks.
Dr. Beyerlein, this is Christopher Wheatley from the University of Kentucky. And I had a question. I saw many spectacular experimental images and data throughout your presentation. And I was just interested in the computational side, if there was what kind of computational data or research there was out there for twinning, particularly, I guess, atomistic simulations, maybe towards the initiation, the nucleation and propagation when you're dealing with a very relatively small scale of atoms.
Right. So, so let's see if I thought I may have something on that from, so here, this is atomistics is a very good way to look at the initiation stage or the nucleation stage. And so atomistics has been used in different ways. One is to analyze, well, what would be the character of the twinning dislocation. While its Berger's vector is fixed, twinning dislocations have a step character as well. So step height has been an important characteristic of the twin. So atomistics have been used to where you take a pre-existing twin boundary and you analyze what would be the kinetically favorable twinning step height. So molecular dynamic simulations have been important for that. And so this has been inspired by, you can see some earlier work where atomistics was not used, but more of this like kind of topological type analysis. There's also been this idea that, well, how does a twin nucleus form and grow? And so here's some work from using atomistics in magnesium. And this is from Wang et al., Jian Wang et al. In Materials Research Letters, where here a stationary large defect was implanted, and then under relaxation, let me put a point. Under relaxation, it evolved into a twin embryo, and then under the growth of this embryo was studied. And what was found by atomistics that wasn't known before was that this twin embryo grows by atomic shuffling, where an embryo doesn't just consist of a boundary of the coherent twin plane, which is theoretical, but there's also been this finding that there's these alternative defects that lie along the twin boundary that can move via atomic shuffling mechanism. So atomistics has been very important for that. Another calculation that has also been revealed by atomistics is this idea that if you were to take intrinsic if you were to imagine you have a grain boundary which contains intrinsic grain boundary dislocations, or let's say misfit dislocations or geometrically necessary dislocations, they've had different names, but the idea is that they're intrinsic to that boundary, but under dynamics, under loading, and with a local stress field applied by, let's say, a pileup, that can cause a reaction of these stationary defects within the grain boundary to then disassociate and create a twin embryo. So atomistics has been very good with giving mechanisms by which twin nucleation would occur. And so that is something that we don't get from a lot of those. I think of some beautiful images are these EBSD images that were taken. That I didn't do them myself, but I'm an admirer of them. And that's something you don't get from just looking at this post-mortem type of images. But what we do get from the EBSD is the variety of different twinning microstructures that you can have. And as those structures, once they reach that mesoscopic scale, that's when those are the twins that are truly accommodating the deformation at that point. And those details of those twinning microstructures do then have an effect on the stress strain response. And so going back to one of the earlier questions was, how do you then unravel, if you have a stress strain response, what are the contributions of different amounts of slip modes and different amounts of twinning modes and different volume fractions and all the twin slip interactions? So there's been over the recent alongside atomistics to try to identify the underlying mechanisms and relative amounts of those mechanisms. So that's different than, I would say, like a continuum scale model, which doesn't provide as much information as more of a micromechanics based model. For instance, crystal plasticity theory falls within micromechanics. And so there's let's see if I have there's been a variety of crystal plasticity or micromechanics based models for twins that are three-dimensional, spatially resolved, and microstructure sensitive. And so I've listed some here that these now pertain to having, once the nucleation happens, now once you get a level where twins have grown to the point they're accommodating deformation, how do we then model that? So while these models here that I mentioned sacrifice some lack of atomistics, that they do then indicate what are the local stress fields and growth of twins, driving the growth of twins within crystals. So this is relatively new. You can see by the dates that I have here. These researchers have developed some of these models. So some of these are just stationary calculations where they just have stationary twins. I would like to point out that this one is nice in that you actually, in addition to having microstructurally sensitive modeling, and you also have some dynamics where the twins will grow dynamically within this. I'm not sure I have seen more on this, but this was a great start. So those are some of the recent tools and findings from modeling. So again, I would say that atomistics is critical for understanding the mechanism of nucleation. One thing is that I think interatomic potentials are constantly being developed here. All of these are magnesium. I think that's where some of the more reliable interatomic potentials lies for the magnesium system. I have to check. I think people are also working on zirconium and titanium. But you are limited to the pure metals for this. Whereas I think one of the benefits of micromechanics is that, well, you do rely on input on material parameters, but they're usually measurable. So I hope that answers your question there.
Thank you.
Yeah. So if there are any more questions, you could speak up, or and we could also discuss. Let's see. I think in some of these, I think you all had very good questions. We could go back to some of the discussion points. Also, Mike, when this lasts, the lecture lasts until 12:20, right? So we have.
Yeah, we have the WebEx session reserved for another 15 minutes, but that doesn't mean we have to go to the bitter end. If everybody's had their questions answered, then we can wrap it up.
Okay, that's fine.
Okay.
Yeah, and so my email is beyerlein@ucsb.edu. So if you have any more questions or want references to any of these, I'd be happy to provide them. So, but thank you all for joining and your interest in this fun subject. So
thank you very much, Irene, and goodbye, everybody. See you next week.
Yes, see you then.
Thanks, Irene. Bye.
Thank you.